Yeah, good evening. Sorry for the delay. I am happy to welcome you all for this webinar. We have with us expert Mr. Jyoti Swaroop. I would like to introduce the speaker to the audience. Mr. Jyoti Swaroop is a mechanical engineer, IIT graduate. He is having close to 50 years of industrial experience. He has worked in various organizations like Nuclear Power Corporation, NPCAL, Engineers India Limited, L&T Valdal Engineering, Hyundai Offshore Korea, Technic Malaysia, Comprimo Singapore, Shemvaga Engineering Singapore, Nippon Steel Construction Indonesia, Emirates National Oil Company Dubai, Gryphon Energy Kuala Lumpur. He is an expert in rotating equipment, piping systems, vibration and noise, pressure vessel, heat exchangers and tanks for farms, for refineries, oil terminals, offshore production facilities, and he is an expert in the ASME standards and so on. You can see his profile also in the screen. He has conducted a lot of training programs, um, offshore, offsite, also in the on-site. So many programs he has conducted in Malaysia, Singapore, plant engineering construction in Singapore, then Dubai. He has been a regular conducting a webinar as well as in-person programs. Without taking much time, I will hand over the dais to Mr. Jyoti Swaroop. Welcome, sir. Over to Mr. Swaroop.
Yeah, thank you, Mr. Prakash. Yeah, I have been conducting many such webinars over the last 8, 9 years, and subjects are basically related to storage tanks, piping, rotating machines. Mainly, these are subjects that I have been covering. I'm sure many of you must have attended at least one or two of these programs. And today's subject is basically design of a storage tank for an specific application, which is sulfuric acid and phosphoric acid. Now, we have been conducting webinars on design of storage tanks as such. So this is more like the specific application of that knowledge for two fluids, which is sulfuric acid and phosphoric acid. Now let me start sharing my PPT so it will give you some idea basically. Yeah. Mhm. Yeah. Can you see my PPT now?
Yes, sir. Please go ahead, sir.
Okay, good. Yeah, thank you. So the subject today is large storage tank design for sulfuric acid and phosphoric acid. Now, why the title large storage tanks? The reason being smaller tanks are usually made in materials like polyethylene, LDP, FRP, etc. But that is not the subject that we are discussing today. Today we are discussing mostly carbon steel, stainless or stainless steel tanks, which are always for larger size tanks because LDP tanks and all are basically vendor made in a specific application. And you have to look at their vendors catalog, basically what is available in the market. But for larger tanks, which are basically site built, this webinar is basically referring to that subject. So we are talking of carbon steel sulfuric acid tanks, applicable ports API 650 and NACE SP0294. Corrosion in sulfuric acid tanks, basically carbon steel tanks, storage tank design as per API 650, and phosphoric acid bulk storage and its construction materials. Now, sulfuric acid is called king of chemicals. Now, I will explain why sulfuric acid is called king of chemicals My brief data Mr. Prakash has already given, so I will skip this now. Now, sulfuric acid applications includes hydrocarbon, oil and gas industry, with the industry where I belong, and is one of the most important industrial chemicals ever produced on the earth. The major use of sulfuric acid is in the production of fertilizers, in petroleum refining to wash impurities out of gasoline, in derivatives, in other refinery and petrochemical products, in processing metals, and in automobiles as the electrolyte in the lead acid storage battery. Whereas aluminum sulfate made using H2SO4 is a chemical used that is coagulant in the purification of drinking water, in paper sizing and other industrial applications in the country. Aluminum hydroxide is made basically from the aluminum hydroxide and sulfuric acid. If you combine the two, it makes aluminum sulfate, which is another chemical used in paper industry and water industry, etc. Now, sulfuric acid is called king of chemicals because of its direct and indirect applications in the manufacture of many chemicals, including fertilizers. Sulfuric acid is used to clean up rust from steel rolls and soap. It also dissolves its compounds. Thus, it is ideal to call sulfuric acid as king of chemicals. Eliminating fossil fuels to rein in climate change will slash the annual supply of sulfuric acid just as demand is increasing. World already uses over 265 million tons of sulfuric acid annually, and a rapid growth in the green economy and intensive agricultural could see the demand rise to over 400 million tons by 2040. So, environmentalists would like to reduce the supply, but agriculturalists would like to increase the supply, and usually it will increase. I mean, it's expected. At one time, the annual production of sulfuric acid in a country was taken as a measure of the economy of the country. Now, uses of sulfuric acid are mostly in fertilizer, 61%, then explosive, non-ferrous metals, etc. Then a lot of detergents, feed, resins, etc. Then some pigments for titanium, paints, linoleum, and petroleum is also one of the users. Iron and steel has one of the users. So these are some of the users that we have in the district, and we are talking of around $49 billion used by about 2032. Now, the two acids, phosphoric acid and sulfuric acid, what is the comparison between the two? Both have a molecular weight 98. One is with 2 hydrogen atoms, other is with 3 hydrogen atoms, according to the P and S characteristics. Now, sulfuric acid is called battery acid, electrolyte acid, fertilizer acid, hydrogen sulfate, etc., while phosphoric acid is also called orthophosphoric acid. Sulfuric acid is a colorless, dark brown, oily liquid, odorless, unless heated, then pungent. Phosphoric acid is clear, colorless, syrupy liquid, odorless. Liquid melting point, sulfuric acid 3 degrees for 98% concentration and 10 degrees for 100% concentration. H3PO4 is solid, often used in aqueous solution, melting point 42.4 degrees centigrade. Boiling point 338 for the sulfuric acid, boiling point phosphoric acid 158. Vapor pressure is very low, while phosphoric acid is higher. pK1 is a parameter called associated dissociation constant, which tells you whether it's a stronger acid or a weaker acid. Now, sulfuric acid is a stronger acid, phosphoric acid is a weak acid. Vapor density is 3.4 for both of them. Liquid density of sulfuric acid is 1.84, while liquid density of phosphoric acid is 1.71. So this is quite a heavy liquid, and any tank designed for such heavy liquid has to take care of its high specific gravity and the corresponding loads which will be applied onto the tank shell and the bottom plate. Now, acid storage tanks. There are various types of acids which are available in the market. So, acids can be hydrochloric, nitric acid, sulphuric, phosphoric, boric acid, etc., etc. And the tank will require to be corrosion resistant material because it is acid. Air venting is a must for all the acid tanks. Size and design has to be suitable to application, and a secondary containment is required so that in case of an accidental release of the liquid does not go out of that area. And durability. Variety of materials including stainless steel, polyethylene, FRP, SLP and carbon steel are used. Standards such as BS 13923, DVS 2205, ASTM, RTP1 give advice on valve thickness, procedures, testing, etc. for the glass reinforced plastic, thermoplastic or polyethylene tanks. While today's discussion is more in terms of larger tanks which can be carbon steel or steel, but just to let you know that IIPE tanks or FRP tanks are available in the market, smaller, relatively smaller sizes, which can be purchased and directly used for storage and transport of the sulfuric acid. Now, sulfuric acid design specificity 1.9. Storage tanks are manufactured from IDP, SLP, FRP, carbon steel. Secondary containment is required, which is a must for the testing. It is best stored out of direct sunlight. Thermoplastic tanks capacities range from 35 to 100,000 gallons. It is about 455 meter cube. 1115 rule is just an arbitrary rule from the vendor to say that sulfuric acid can be stored in tanks less than 11,000 imperial gallons and less than 15 feet tall and high density cross-linked polyethylene tanks or high density polyethylene tanks. So typically smaller size tanks, maybe less than 50 meter cube or less than 4.5 meter high, we can buy IDP or SLP tanks or FRP tanks, but larger tanks, these tanks may have to be site built, and therefore, we need a steel material, carbon steel or stainless steel or some other material. Maximum service temperature of IDP tanks is 130 degrees Fahrenheit, which is 55 degrees C. So this is a limitation, while carbon steel or stainless steel does not have this kind of a limitation. Now, the course that we talk about, API 650, talks about the steel tanks, basically, and vertical, cylindrical tanks. So, carbon steel tanks are reported to be most effective at storing high-end concentrated sulfuric acid solutions of 93% and above. You can see some of these photographs which are here for this is how the storage tanks look like. If you see some of the things that we will talk about is, let us say, this too. If you see the foundation is not on a typical foundation, but on beams. To make sure that any leakages from the tank can be seen and can be controlled. The water content of any concentration below 93% will allow an increase in corrosive activity on carbon steel storage tanks. Therefore, only above 93% we prefer to use, even though tanks are used up to 77% H2O solution, but it is assumed that 77% H2O or higher up to 93, the tank will corrode. So tank corrosion is taken for granted in tanks which are of a concentration say 77 to 93%. And the tanks, that means, have to be regularly monitored to make sure that the corrosion does not exceed, to the extent that it starts creating a problem. Now, it will still cause gradual corrosion. Regular tank inspections and maintenance are important for maintaining carbon steel sulfuric acid tanks. Now, of additional storage concern, this reactivity between carbon steel and H2SO4 can generate hydrogen gas and iron sulfate in the formula Fe plus H2SO4 is equal to FeSO4 plus H2. So the protective layer of FeSO4 prevents the metal from a new attack by the concentrated sulfuric acid. Therefore, the durability of tanks and pipes made of carbon steel will depend on the preservation of the FeSO4 layer. So this has to be very clearly understood that unless that protective layer is formed on the tank and that layer remains there, the tank will corrode very fast. So in carbon steel tank, when you put sulfuric acid, initially there is going to be corrosion, there is going to be rusting of the surface, inner surface of the tank, which will form FeSO4, and that FeSO4 formation will not allow further corrosion of the tank. So this is how the carbon steel sulfuric acid tanks basically are utilized into the industry. Now the problem today is hydrogen gas is flammable and buildup of gas can be potentially explosive. Venting systems are a requirement for carbon steel and sulfuric acid to prevent accumulation of hydrogen gas. Thermoplastics such as PVC are the recommended materials for sulfuric acid vents. Steel vents are not recommended due to potential for iron sulfate reaction and buildup of the vent pipes. Iron sulfate is a precipitate formation that will settle within the sulfuric acid solution in tank system, and buildup of iron sulfate is a purity problem, and accumulation can cause problems in piping runs or pumps. So accumulation also gives the impurity into sulfuric acid, and if the quality of sulfuric acid required is higher quality, then carbon steel is not the suitable material for the application. And then we have to use some other materials like HDPE, FRP or stainless steel, etc. Now images of carbon steel ring in concentrated 96% region grade H2SO4 of 25 steel. If you see these photographs here, immediately after the immersion, the formation of a large amount of hydrogen can be observed. So if you see this photograph is here, before immersion, then immediately after immersion, hydrogen is formed. After 30 seconds of immersion, after 1 minute of immersion, complete hydrogen is formed. After 15 minutes, FeSO4 is formed, and hydrogen generation is reduced. And finally, after 24 hours, there is no hydrogen generation. So this is how this behavior, happens into a carbon steel tank. And after 24 hours emission, a strong decrease of metal attack is observed because of presence of dark protective layer of FeSO4 on the metallic surface. So this is the basic principle on which these carbon steel tanks are built and utilized. Now, in 2022, the market volume of sulfuric acid worldwide was 265 million metric tons, and a forecast for 2026 is almost 294 million tons, while in comparison, phosphoric acid market is only 61 million tons in 2022. So you can see sulfuric acid is a very large volume liquid which is traded in the international market. India imports a lot of sulfuric acid from other countries because India's market volume is almost 17 million tons, which is only a fraction of the world market. Sulphuric acid is the largest volume corrosive in use today and is generally considered most important industrial chemical. Large storage tanks containing sulphuric acid and oleum are located in many areas. Now, oleum is defined as a liquid wherein sulphuric acid also contains free sulfur dioxide. Thermal steel corrodes moderately when in contact with concentrated sulphuric acid or oleum. So, dilute sulphuric acid is more corrosive than concentrated sulphuric acid. So, if properly designed and adequately maintained, use of carbon steel is an economical option for storage of these acids at moderate ambient temperature, especially for large sized tanks. Now, what are the design factors that we need for control of hazards? Location of storage tanks related to other chemicals and working areas. Tight system that minimizes the chances of sulphuric acid leaking and endangering people. Means of confining accidental leaks as well as proper drainage and cleanup of tanks, cleanup of leaks and spills in a manner consistent with plant and regulatory agency requirements. Provision for more than one escape route in the event of fire, explosion or release of H2SO4. Easily accessible safety showers, firefighting and other emergency equipment, and provision for venting, storage and unloading facilities to a recovery or abatement facilities. Then sulphuric acid should be stored in a cool, dry area away from direct sunlight and heat sources. Acid is not to be sealed between two closed walls and a thermal release valve discharging to a safe location must be installed. Storage should be open or well-ventilated area. This is to prevent possible accumulation of vapors. Tank foundation should be slightly above grade and slope to facilitate drainage away from the tank, and vertical tank should preferably be mounted on drill edge to minimize potential for external corrosion of the tank bottom. Because one of the biggest problem becomes is tank, if it starts corroding near the bottom, then you will not know if it is sitting on a concrete foundation. So usually the acid tanks are put on I-beams or on concrete beams to make sure that any leakage is seen, can be detected and corrected. So this is what we call grillage. Grillage is the word for used for that. And most of the sulphuric acid tanks will be installed on grillage. Now, large vertical sulphuric acid storage tanks are usually built to API standard 650, which is welded tanks for oil storage, and horizontal tanks built to ASME pressure vessel code. While these standards provide for sufficient material strength and toughness, they do not address the peculiarities of the corrosion by sulphuric acid and oleum. Therefore, certain allowances in the design for corrosion control in these standards are left to the individual designer, owner or operator, and that is where we use NAIRS SC0294 code, which is for design, fabrication, inspection of storage tank systems for concentrated flushed and processed sulphuric acid and oleum at ambient temperature. This provides recommended design, fabrication, and inspection practices for maintaining the mechanical integrity and minimizing the potential occurrence of undetected corrosion. At inlet temperature greater than 40 degrees C, or if tanks has heaters, material engineers to be consulted to design material of construction. The NAIRS code is applicable for concentrated fresh sulphuric acid vertical and horizontal tanks, processed sulphuric acid tanks, or oleum storage tanks at atmospheric pressure and low pressure. Applicable code can be 650 or API 620, which is less than 100 kPa pressure. Spent sulphuric acid tanks from alkylation units are not within this standard and are covered under NAIRS RP 0205. I will be referring to many such niche codes today when we continue the discussion, which are useful in designing the tanks, especially for the steel tanks. Inspection guidelines that aid in detecting and monitoring corrosion are presented with the overall aim of being to avoid catastrophic failure. Now, I have given some definitions here: what is fresh acid, what is processed adenoid, what is oleum. Just for reference, if you want to get a note, you can request for it. Now, typical tank design. This is from the NACE code, basically, which says the support design, inlet, outlet, vents, membranes and side nozzles, rear plate, roof, level control, heating systems, and bottom plate thickness. So these are the subsections for the design of the tank, basically sulfuric acid tank, as given into the NACE code. As you can see, the inlet is from the top in most of these tanks, not from the side. The roof to shell joint has to be properly done. Support the dip tube for the inlet pipe has to be supported. Top membrane vent is a must for it. Overflow requirement. Side membrane, outlet, side outlet, or bottom outlet, depending on what you want to prefer. So these are some of the details given into this code, and we will discuss some of these criteria from the code, not all of it. For a complete detailed design, a reference has to be moved to the respective code. Now, for vertical tank, which is a figure that we just now showed, figure C4, one of the two alternatives presented in paragraph 3141, 3142 should be used depending on tank diameter. For tanks up to 12 meter in diameter, there are two options for tank support. Tanks must be supported on a raised, reinforced concrete slab foundation that is sloped and groomed to drain any water or leakage. Tanks may be supported on steel I-beams for improved leak detection, and beams are frequently set on concrete piers. While I-beam support, rainwater or acid spillage may collect between the I-beam surface and tank bottom, resulting in local crevasse corrosion of the tank bottom. So these are two things which has to be taken care. For larger tanks, a concrete ring wall foundation with compacted granular fill and clean washed sand topping may be used. Larger tanks may be installed on units. It may be more economical to use compacted granular fill sand instead of units. For tanks on concrete foundation, a suitable skirt may be considered to prevent water from running under the bottom. So if you see this kind of a skirt that you see here, to minimize water below the tank bottom. Because tank bottom corrosion you can't see unless you want to empty the tank and do the inspection there. And not only must the foundation adequately support the weight of the loaded tank, it must be designed to keep the bottom of the tank dry. This is the most important criteria. And wet foundation can lead to external corrosion in the form of general metal loss or localized fitting. There are generally three types of foundations commonly in use. Reinforced concrete slab foundation, which is the top figure that you can see here. The other is steel I-beams and concrete support. Third is concrete ring wall foundation. So for large tanks, we can use ring wall foundation, and we'll have to have methods of monitoring the leakages below the tank. So these are three different types of foundations which is possible. Now inlet nozzles. So we are talking of only accessories of the tank. We will talk of the basic tank design also as we proceed with the presentation. So inlet nozzles, there are specific requirements for inlet nozzles to be used in the sulfuric acid tanks. And tank shall be fitted with a top inlet nozzle protruding at least 150 millimeter into the tank if a dip tube is not used. If a dip tube is used, the top inlet nozzle may protrude only 25 millimeter into the tank. So the idea being is that the acid should not touch the roof. When you want to, when you are putting in the acid there, roof plate should be independent of the inlet nozzle so that there is no corrosion onto the roof plate. So these are the code, the figures given into the code which can be utilized into the design. Now, inlet nozzles for vertical tanks, the top inlet nozzle should be as close to the center of the tank roof as practical to reduce side wall attack. Because any inlet nozzle near the side wall will attack the surface of the side wall and that may start corroding preferentially, and that should be avoided by putting the nozzle inside, deep inside the tank, more closer to the center of the tank. So minimum distance should be 1.8 meter away from the side wall, and a wear plate is needed below the inlet pipe. Corrosion resistance allow construction should be considered for inlets on new construction or retrofit tanks. So this is the area which will be, corroded if you have a nozzle close to the, close to the shell, then the liquid will be falling onto the shell plate, and then this area need to be monitored by whatever means to make sure that there is no corrosion into this area during the operation. Outlet nozzles can be side or bottom, and it can be, outlet nozzles could be with a bend as you see in the top figure C9, or bottom directly, or a side nozzle. But side nozzle design has to be suitably done that any liquid does not touch the shell plate in any way. And velocity criteria given in the other NACE code, which is NACE 391, should be considered when siting the outlet. Typically, the velocity should not exceed 0.9 meter per second for carbon steel and 1.8 meter per second for stainless steel tanks. The outlet nozzle's external outlet valve should be fitted as close to the tank as practical. It is necessary to provide an outlet elbow before the valve, which shall be long radius type with an extra heavy valve. Corrosion resistant alloy construction is often used for piping and elbows between the tank outlet nozzle and the first valve. Outlet piping should be protected from mechanical damage that could impact the tank system integrity. Wear plates beneath the inlet outlet pipe should be seal welded to the bottom of the tank. Now, roof of the vertical tank. The roof should be sloped and self-supporting. Roof support girders should be installed externally. If you see these photographs here, this is the roof support. The girders are basically installed outside the tank, not inside the tank. You see there, mostly API 650 tanks, these girders are inside the tank, so easier to construct. But for sulfuric acid, to make sure that these girders don't corrode, they are installed outside the tank, which is more difficult to construction. For large diameter tanks, internal support columns are accepted if required. Adequate corrosion allowance is provided for the internal support columns. Open section columns are preferred over tubular section. And consideration should be given to adding a corrosion allowance of 3.2 to 4.8 millimeter with a roof plate. Now, tank vent, as you can see here in the center, there is a tank vent always provided. And tank vent shall be located at the high point of the tank, which is center of the roof, to allow entire volume of tank to be vented. Why venting is so important? Hydrogen generation may create an explosive environment in the tank, which must be avoided. So, sulfuric acid storage tanks must always have an open vent for normal breathing and to prevent dangerous pressure buildup or formation of an explosive mixture due to hydrogen, and vent line must be constructed of acid resistant material. If you construct it with carbon steel, it may corrode and even close. So hydrogen gas may be produced from action of acid on the steel tank and cause an increase in pressure to form an explosive mixture. The vent should be at least same diameter as the fill line, the discharge line, or the drain connection, whichever is greater. Preferably, the vent should be one pipe size larger. Now, periodic documented inspection of vent line for blockage may prevent tank collapse during acid transfer, because when you are extracting the acid, the air has to go inside. When you are loading the tank, the air has to go out. So the vent has to be open all the time, and if it is not open, then it could create a problem of pressure or vacuum. The vent can be equipped with a gooseneck vent, as you see in this photograph here, or point straight out to protected with a cover of prevent entrance of rainwater. The vent opening should be equipped with a bird screen to prevent animals and foreign objects from entering the tank. Now, consideration must be given to the advantages and disadvantages of desiccator vents compared with open vents. Now, what it means, we install a desiccant dryer onto the vent if it is required, so that study has to be made, because sulfuric acid may start absorbing the atmospheric humidity. Air draws may be desirable when there is high humidity and a low turnover rate of the tank contained. If the tank is located indoors, the vent line should be extended outside the building. Installation of air dryer is optional. Vents should be inspected periodically to ensure that they are not blocked. So the reason being, sulfuric acid is hygroscopic, which means that any moisture entering the tank will be absorbed in the top layer of the acid. Over time, the top layer will become diluted, more corrosive, and will give off heat as water is absorbed. So if the area is highly humid, then it is advantageous to put a dryer, desiccant dryer or something equivalent. And one of the vendors, item I have shown here, desiccant dryer from one of the vendors, which are the most common way of preventing ingress of moisture into a tank. The size of dryer required to protect the tank is determined by the amount of air and the rate at which air enters the storage tanks, and desiccant should be sized to last from 1 to 6 months per charge. So every time you want to, empty the tank, the moist air will get inside, and that moist air is dry. Similarly, when you want to load the tank, the vapor with acid vapor will be absorbed by the dryer. So both ways the desiccant dryer will work in both in and out of the air. Now, hydrogen glowing is one of the typical problems that you see in the sulfuric acid tank. What if we see the basic formula H2SO4 is iron equal to Fe2 H2? Now, sulfuric acid tanks may have hydrogen glowing in manhole upper half area. Remember this, manhole upper half area. The reduction of hydrogen ions to form hydrogen gas may be expressed as 2H plus 2 electrons is equal to hydrogen gas, and that change in the ion to the gas, the complementary reaction of oxidation of steel is Fe2 plus 2 electrons gives you Fe. And that hydrogen from general corrosion collects in the upper half of the membrane, and that membrane starts producing, blooming like this on the top of the membrane, and this needs to be avoided. And the damage occurs as a result of hydrogen gas forming and steaming of the manhole, disrupting the loose iron surface passive film. The blooming can cause localized corrosion allowance consumption fairly rapidly. See also 2814 of this thing code for details. Corrosion resistance allows to be used in areas susceptible to hydrogen blooming. So as you can see, the hydrogen getting collected near the top of the manhole, and that hydrogen removes the where sulfate, hydrogen, and more hydrogen is produced because of that, and this forms grooving like this into the top of the nozzle. So what we do is to protect the manhole and the nozzle by putting additional material into the tank, into the nozzle. So what you call next SP0294 says these are two diagrams for side outlet and C2 for side mainways. Mainways and side nozzle shall be flush to the cell internal surface on bottom 180 degree and should have a minimum 25 millimeter visor on the top 180 degree to force any hydrogen bubbles away from the side wall. So this kind of a visor is normally installed into the mainways of the nozzle to make sure that the mainways do not have this kind of a grooving problem. So these some of the protective designs that we made when we are trying to design a sulfuric acid tank. I will just take a 5-minute break and we will join after 5 minutes. So just give me 5 minutes. Okay? Yeah. Yeah, I'm back here. Yeah. Now we are talking about basically inlet, outlet, support, etc. for the tank as per SP 294 NIST code. So this is one of the most useful codes for designing of sulfuric acid tank. We talked of FES support formation of the tank, which protects the tank from corrosion, but any breakage of this iron sulfate, the tank again starts corroding and the breakage of this iron sulfate has to be minimized or eliminated if possible. So there is too much interference into the too much of turbulence into the liquid, then the corrosion will start increasing. So let's talk of corrosion mechanism of carbon steel and H2SO4 tanks. In dilute sulfuric acid, attack on carbon steel takes place with the formation of hydrogen gas and ferrous iron in the below equation. Anodic reaction is Fe is equal to Fe2 plus 2 electrons on ferrite phase of carbon steel. Cathodic reaction is 2 hydrogen plus 2 electron gives you hydrogen on cementite phase of the carbon steel. So look at the microstructure of the carbon steel. There are different behaviors on the ferrite and the cementite phase, and this hydrogen may cause grooving of the internal tank walls that we talked about. The damage is most prevalent near the upper half of the manhole and nozzle. Now, corrosion of the carbon steel in sulfuric acid starts the ferrite cementite interface boundary. Now, what we can do is we can prevent this corrosion by putting anodic protection. System installed on large tanks are very cost effective. Now, I'm sure many of you have heard of cathodic protection for storage tanks, but acid tanks, the cathodic protection may not work because it will require very large current for the cathodic protection. Therefore, we have a system which is called anodic protection of the storage tanks, which is different than the cathodic protection of the tanks. And this anodic protection needs to be installed, especially in larger tanks, if we want to avoid the corrosion into the tanks, especially large tanks. Because the cost of the tank's replacement or the maintenance is quite high. To minimize the corrosion, we can provide anodic protection, which is something similar to the cathodic protection that we all know into the other tanks. Now, corrosion allowance is again because we know the tank is going to corrode. The corrosion allowance values definitely are much higher than a typical tank that we normally use API 650 or IS 803. And new construction corrosion allowances for carbon steel tank and nozzle surfaces wetted by sulfuric acid, oleum at ambient temperature are given in this code. And depending on the SPSO concentration, 70 to 80%, 80 to 88, 88 to 99%, 99 to 96, 99, and more than 100.5, which means oleum basically. The minimum corrosion allowance typically used is 6 millimeter, 6.4 millimeter, or for oleum and all it is 3 millimeter, which is good enough for this is what the recommendation from the code. So corrosion allowance will adequately address the concentration, temperature, normal excursion and design life, and corrosion rate will greatly accelerated under flowing turbulent conditions. Now these corrosion allowances are for the static conditions. If it is flowing liquid, then these corrosion allowances have to be increased. And we can see it from the code called API RP 581 Annex 2B Section 5, which also we will discuss around. Now, still corrosion by fresh stagnant sulfuric acid, no flowing, as a function of concentration and temperature. This figure is copied from the SP code. Now, as you can see, the corrosion rises with the increase in temperature due to increase in solubility of FeSO4 layer. Example, 70% acid at 24 degrees is only 0.5 millimeter per year, while 107 degrees C is 10 times of 5 millimeter per year. So corrosion rate has to be established, and accordingly material of the tank has to be selected, or necessary method to avoid the corrosion has to be installed. For example, anodic protection that we talked about. So, material selection and corrosion allowance both are important criteria for the design of the sulfuric acid tank, depending on the application and the uses that we have. It's a very regular uses, or it's only a once in a while that you unload and load, then the materials could be different. And many times you may not be able to use carbon steel if your temperature is high or there are other criteria. Then you use corrosion resistant alloys, things like nickel-based, materials, which can be, given as per the code. Now, NXB gives all this depending on the concentration of the SPSO4. Different nickel-based materials are mentioned. For 90 to 100.5%, SS316 is also good. 93 to 100.5%, 304 also may be good. So these are different, as you know, 316 is more expensive and liquid-based alloys is still more expensive. The most economical solution obviously is carbon steel, but if you cannot use carbon steel, go for 304. If not, then go for 30316 or nickel-based alloy. So it increasing cost, range, you have to look at the specific, application that you have and the concentration you have, temperature you have, how often you are using it, loading, unloading, and so on and so forth. There are other codes also like Nickel Institute, it says allow selection for service in sulfuric acid. So a lot of these references I have mentioned here for use if you are actually designing a tank for sulfuric acid. The corrosion rates given in millimeter per year and steel relative cost for carbon steel 304 and 316 because as I mentioned carbon steel is the cheapest material, 304 is up to that and 316 is still more cost. If you look at the Article 581, depending on that each table for different materials corrosion rate depending on the flow velocity and temperature and the concentration. So these tables have used only the static flow 92%, 98% and given the values of the corrosion rate millimeter per year. So if you see here for carbon steel, if you're talking of say 98% SPSO4, 33 degrees, 1 millimeter per year. That means if you provide 6 millimeter corrosion alone, your life of the tank is only 6 years, which is not what we are looking for. So we need a longer life, say 20, 30 years of the tank. Then suitable material has to be selected depending on the application. It's very important. Now we know the cost, relative cost of these materials is just a relative numbers. Don't take these numbers as correct numbers. For example, carbon steel something like 720 US dollar per ton, while SS is 316, 316 is 4602. So these are typical rates of the carbon steel, stainless steel, and depending on the application, you have to select a proper material that is applicable for a particular job that you are talking about. Now this is the other code which is next MP 391 material for handling and storage commercial concentrated sulfuric acid at ambient temperature. So we have a separate code for material selection only. And I have just given a brief description of what does it say. It can use carbon steel, cast iron, stainless steel, high nickel stainless steel, other alloys, non-metallic materials. And non-metallic, as I mentioned, is for smaller, sizes. For larger sizes, you have to go with the carbon steel or other steel. The other things also come to rail tank cars because a lot of sulfuric acid is transported using rail tank cars. And the design of piping, walls, pumps, gaskets, etc. materials have been specified in this code. And commercial acid is usually stored at 93%. And sorry, I don't know what I mean. Here. Now, freezing point is another interesting criteria of the sulfuric acid depends on the concentration. So if you see the concentration of acid discharge at different temperatures and different concentrations, the freezing point is not a very smooth curve. It's a very funny kind of a curve that you see here. And acid concentration something like 36%. The freezing point can be minus 50 degrees, but acid concentration at 100%, the freezing point is 10 degrees. So that means if you have a minimum ambient temperature of 4 degrees in a Delhi environment or wherever that you have, then the sulfuric acid will freeze in the tank. And accordingly, we prefer to use something like 93% concentration, because that has the freezing point something around minus 35 degrees C, which means there is no chance of freezing into the tank. So this freezing point is very interesting curve. If you see, this is going up and down, all kind of a random behavior is there, and we have to make sure that if the tank there is a chance of freezing the liquid, then you have to provide heaters into the tanks, and heating and insulation of tanks and piping as applicable are recommended or required to prevent freezing of the tank sulfuric acid depending on the concentration that we have and the freezing point curve that is shown here. Now some applications of sulfuric acid. Production of phosphoric acid is a main application. The fertilizer basically this phosphoric acid is converted into fertilizer, commonly regarded as the main source of conventional sulfuric acid. The wet method of producing phosphoric acid is used for manufacture of phosphate fertilizers, which can be DAP, MAP, SAP. Rock phosphate of fluoropatite is treated with 93% sulfuric acid to produce calcium sulfate, hydrogen fluoride, and phosphoric acid. Iron steel manufacturing is used to remove rust, scaling, and other forms of oxidation from gold, steel, and billet before using for manufacture of automobiles and other applications. Most sheet plants consist of spent acid regeneration units, wherein spent acid is burnt with natural gas, refinery gas, or other fuel sources, which produces sulfur dioxide and sulfur trioxide, which are then used to produce new sulfuric acid. So manufacturing of ammonium sulfate is also another usage, and nitrogen fertilizer that is produced in mass scale by reacting ammonia with sulfuric acid, where ammonia is converted into ammonium sulfate, which gets crystallized and separated by centrifugal or filtering process. Now, manufacture of aluminum compounds is another application of sulfuric acid, which can be aluminum sulfate to produce large scale in paper making industry. Aluminum oxides are purified into aluminum soap on paper pulp fibers. Adding sulfuric acid gives gelatinous aluminum carboxylate, which coagulates the pulp fibers into hard paper surface. Then sulfate is also a coagulant for water purification, sometimes used as a catalyst or even used for dye listing. So this was generally about the tank special requirements of the sulfuric acid tanks and the applications. Now there is also a possibility of providing lining into the carbon steel tank, and there are certain clauses into the code which say high temperature baked phenolic linings and epoxy novolac linings are commonly used in small carbon steel storage tanks if iron contamination is a concern for sulfuric acid in 90 to 98% concentration range. So this can only be used in smaller tanks for the simple reason it has to be a baked phenolic lining. Baked phenolic lining is important, and baking is only possible if you can use a small tank which can be put into a furnace. So tanks are being considered for lining should be small enough that lining can be baked. Tank fabrication, surface finish and design shall be complied with NACE SP 0178, which is the code for lining of the tank. Now that is why carbon steel tanks are usually not utilized for small sizes. We use HDPE or PVC or FRP tanks. Because if purity is a problem, then HDPE tanks probably will be a better solution than a carbon steel lined tank. But this option is also available. Proper application in curing must be ensured to achieve long service life, normally experienced in sulfuric acid service up to 98%. See, concentration is so important. What concentration you are designing it for, and accordingly the material selection and design comes into the system. So SP2592 code is there. Application of coating systems for interior surface of new and used rail car tanks in concentrated sulfuric acid service. So there are specific codes available for coating system design and detailing can be seen into the respective codes. So tank design. The tank design is same as any other tank design for hydrocarbon or water or something. There is no difference. Now I'm just covering it quickly, which can be as per API 650, or if it's an Indian project, then it will be as per ISA 03, which is the equivalent code for the API 650 used in India. So for instance, like a detailed calculation for tank shell, bottom and roof plate sizes, thicknesses and quantities required for given tank diameter, height and liquid specific gravity, include design of wind girders needed for stability of shell plate. Example problem with 20-meter diameter tank and 16-meter height concentrated sulfuric acid tank is also included for reference. Now this is how the plate will look like. Shell plate, if you take shell plate, this is how the shell plate will be organized when you want to join it. This is like you open a shell course and open it in a flat, this is how it will look like. And you can see the bottom course of the shell plate will be the highest thickness, the top course will be the lowest thickness among the two. And you can see this is how the tank will look like. The tank plate will look like depending on the plate size. Each plate is welded to other plate in both horizontal and vertical direction. This is how the tank plate will look like when you see it from a side of distance. The tanks also require nozzles, shells, roof nozzles, roof hatches, roof platforms, stairways, manways, etc., etc. And a fixed roof tank, which is what is required for the slope will be required for the bottom of the tank, and such details has to be worked out, which is irrespective of whether it is a sulfuric acid tank or a hydrocarbon tank. So we will talk very briefly about this design, and probably a separate webinar was there, which was probably some of you have attended, for design of the storage tank. Now, typical bottom plate layout of a tank is looking something like this. The plates are arranged staggered from each other. The edges may have what you call the annular plates, and on which the shell is actually resting. Here are some welding details of the three plate joints that comes into the plate to plate welding or three plate dimensions, or a shell to bottom plate welding, which is on an annular plate. So all these details are a part of the API 650 and the ISA 03, which can be seen into the respective codes. Now, a typical tanks will have, rafters, girders, and columns. So rafters are radial members or steel members for supporting the roof. Girders are the circumferential members, and vertical columns are, if they are required, then vertical columns. So this is typical tank roof components is rafters, girders, columns, and these need to be designed for the sulfuric acid tank also. The rafters and the girders are external to the roof. For acid tanks, very important. This is how the structure may look like for the roof if we are designing it. The typical storage tank design for sulfuric acid I have given here in these few white, you can see these calculations here. For a 5,000 meter cube with a sample calculation, 20 meter diameter, 16 meter height, cold to flow 1:12, shell plate, transport millimeter, thickness is 24 and 10, bottom plate thickness 16 millimeter. These are final conclusions of design, and so on and so forth. The code used is 650 and design code is made SP0294 for a design wind velocity of 160 meter cube per hour for a 98% sulfuric acid. So we are talking of this tank design as we proceed into these 7 slides, which are for tank design. There's nothing specific for the sulfuric acid in this slide. This is the standard tank design of any kind of a tank, whether hydrocarbon or water. Except that the accessories for sulfuric acid will be according to the NACE SP0294 code. Now, corona allowance is taken from NACE standard table 1, 6.4 millimeter, which is for bottom shell plate and nodules. In case anoded protection is provided, it may be 3 millimeter. Maximum operating level considered 1 millimeter below the tank top. Our hydro test is considered full height. Material of construction considered is IS 2062 grade A, which is historical grade for India, and higher grade may have been considered, which will reduce the thickness of the plate. A plate size, what is available in the market, may be 2 meter by 6.3 meter, which is the example I have taken. Usually we take larger plates to reduce the welding. Is selected based on the availability, number of shell courses depending on plate width. So if it is 2 meter wide and a 16 meter high tank, we require 8 courses. This is what is said in the design, 8 courses. So you see this tank 1, 2, 3, 4, 5, 6, 7, 8. This is how the courses are designed. And the circumference, you take the length, basically 6.3 meters. So whatever circumference, you put number of plates into the welding. Now, API requires minimum plate width of 1800 millimeters. So I have selected a 2 meter wide plate, or it should be even higher. Required shell thickness shall be greater of the design shell thickness, including corona allowance for hydrostatic case or design case. But since the hydrostatic case in this is for a density of 1, in the sulfuric acid case, it's only design thickness which will be applicable because specific density used is 1.9. So allowable stress is being taken from the code API 650 from the table 5.28 or Indian standards like 2060 was calculated based on the formula given in API 5621. And I have calculated the allowable stress for design 160 MPa and for hydro test 176 MPa, and calculation of shell thickness by 1/5 method is done using this formula. So you can say 4.9 D H minus 0.3 G by HDE plus corona. D is diameter, H is height, G is the specific gravity, E is the efficiency of the joint efficiency, and T is the design allowable stress, ST is the hydro test allowable stress. Now in this case only design stress will be applicable and the thickness calculated will be much higher than the hydro test stress. So this is how we do the calculation for the thicknesses of each shell course. We go one by one, first bottom, then next up to the last shell course. And add corona allowance to it, and that gives you the calculated thicknesses. Now this simple calculation has given this calculation, which can be utilized by anybody who wants to design a calculation as a reference. So each shell course plate thickness is calculated for design and hydro-test case. Design thickness is much higher as a method shell thickness by variable design point method given in API. This gives slightly different thicknesses, like in this case, variable point method is giving you slightly higher thickness, only 3% difference. But you normally take a margin of 6 millimeter as a corner allowance. So normally it will not make a much difference in the calculation. Now other item which comes is wind girders. Now wind girders are basically the additional stiffening that you provide onto the shell, which you see it here. Those wind girders also need to be designed in the larger tank to make sure the wind loading does not affect or damage the tank. And wind girders unstiffened shell height can be calculated using this formula given in the API code, which is thickness into TQ, T by DQ, 1.70 divided PWD, where P is the wind pressure at 10 meters above the grade, and all these parameters are, as we say, height of the exponential, D is the diameter, and V is the velocity, joint wind speed, which needs to be worked. So all these numbers have been worked out for corroded and uncorroded conditions of the shell plate thickness. But the shell has to be suitable for the life of the plant and it is going to corrode. So the thickness has to be calculated for the corroded thickness and accordingly wind girders has to be provided. And if we do not provide wind girders, then what happens during the construction itself? The tank itself will get damaged due to the high wind load. So the design of wind girders is extremely important for the integrity of the tanks. And in this calculation, what we found is wind girders are required 2.6 meters below the top curve angle, which was not required for uncorroded thickness, and selected member wind girder size was L-shaped channels 125 by 75 by 9 millimeters. All these calculations are given here in this calculation field. So bottom plate and roof plate thickness is again taken based on API 650 guidelines. Example here shows how arrived at bottom plate thickness of 15 millimeters with a corner of 6 millimeters and roof plate of 8 millimeters. Roof rafter support details may need to be arrived at based on roof structural analysis. We use Step Pro or ANSYS software for this. Suggested rafters is 32 numbers for a tank diameter 20 meters. You can see these rafters which are here. So this all design is a part of the tank design and these radial numbers of our rafters, the 32 numbers have been selected because the code requires a minimum distance between rafter to rafter at the periphery of the tank. So maximum rafter spacing near tank periphery is required to comply with API formula 5104 and the shell top angle is still selected based on API criteria at 100 by 100 by 10 millimeters. This is what we call as top angle, and this is the intermediate wind girder that you see there into the tank. And tank plate thickness you can see bottom is the most thickest plate, then top is a thinner plate. As the pressure keeps on increasing at bottom, the plate thicknesses keep on changing. The shell top angle is selected based on API criteria. Shell bottom and roof plate MTA is taken based on shell periphery and base area for given plate size. The plate will be different number of shell coating width. So you calculate finally how many shell plates are required. So 24 thick 10 plates, 22 thick 10 plates, and so on. You calculate the quantity, calculate the structural quantity, and that will give you the proper MTA for the tank design. This is the output that you get from the tank design detail. So this was a very brief discussion about the tank design for sulfuric acid tanks. And if you want to go into the details, I have other presentations which are more details regarding the tank design. So secondary containment is another important criteria wherein essential lines of defense in the event of failure of primary containment such as bulk storage container, piping, a mobile or a portable container, or oil-filled equipment. All sulfuric must contain secondary containment. Common containment for bulk escape through complete diking with an acid resistance coating as concrete will react with sulfuric acid. Secondary containment should be capable of retaining at least 110% of the tank total volume. So this was all about the sulfuric acid tanks. I have covered here few of the phosphoric acid tank details, which is not as corrosive as the sulfuric acid tank, but as you saw, it has almost similar properties, but less corrosive than sulfuric acid. And phosphoric acid is also quite a large volume in the global market, $49 billion in the 2023, and this is increasing to $52 billion in 2024, and could be even higher, $66 billion probably in 28. Now, generally, stainless steel tanks found in chemical tankers are resistant to phosphoric acid tanks. However, excessive fluoride within the phosphoric acid can initiate corrosion attacks, allowing for continuation of attacks by the phosphoric acid itself. So fluoride content of the phosphoric acid needs to be monitored even though we use stainless steel tanks for the phosphoric acid. So primary considerations in the design of bulk storage and handling are corrosive properties and freezing point. So freezing point is much more critical in phosphoric acid than it was in sulfuric acid time. And freezing point varies greatly with the acid concentration. Again, these are freezing point chart that you see here. Freezing point is the reason being is also subjected to supercooling. Well below the freezing point, if there is no sheathing or agitation, for this reason, 75% acid can be stored outside with little danger of freezing. As you can see, 75% of freezing point is minus 30 degrees, so not an issue. 80 to 85% acid gas may require some form of heat to keep them above their freezing point and depending on location or system. So freezing point is an important criteria and depending on the concentration that you are designing it, we have to look at the material selection and the heating of the tanks if so required. For the now, for construction material, all the service conditions must be considered when selecting the material. The factors are concentration, temperature, vacuum service or static storage, solids in system that may cause abrasion, heating coils in the tank. Stainless steel is a preferred material. 316L is used for storing all grades of phosphoric acid, especially desirable for food grade acids. To avoid welding difficulties, extra low carbon acid is used. 15 to 30 ppm chloride will increase the aggressiveness of acid to stainless steel enough to increase the Fe, nickel and chromium content in the acid and impart color to the product. Isochronic charge of 316L in phosphoric acid is as shown. Some vessels ship tanks for phosphoric acid transport have SS317L in the vapor space in the bottom and 316 for the remainder. 317 is a material with higher molybdenum and higher chromium, thus higher corrosion resistance than 316L. Now, other possibility is to have a rubber-lined steel tank, so which also has good corrosion resistance, less expensive than stainless steel. Pure natural gum white rubber and fluorobutyl rubber are recommended, though resistance varies with manufacturers. Fluorobutyl, a synthetic material, has good resistance to phosphoric acid, elevated temperatures and low rate of permeation. New rubber lining often imparts some color to the phosphoric acid, which will drop in an undetectable level after stored several cycles. Most phosphoric acid manufactured stored at elevated temperatures may range from 60 to 93 degrees C and concentrations 28 to 70 degrees is highly corrosive and needs suitable rubber lining to give desired service line. The other option is to use fiberglass reinforced plastic FRP, which can be used and performance of fiberglass tanks surpasses that of rubber lined tanks and nearly equal that of the stainless steel tank. Most pronounced advantage of fiberglass is one initial cost. Fiberglass tanks are less expensive than rubber lined tanks and can cost one-third as much as stainless steel. Bisphenol is accumulated to the recommended polyester resin. Below the steam coils and FRP, and of course not recommended as glass-lined steel or 316SS, only 316L can be used for carbon steel. But nickel-based alloy selections are also possible for the phosphoric acid tank. Now, a typical phosphoric acid take example I have taken from a FETO document. FETO is fertilizers and chemicals Travancore engineering and design document. So we see the drawing here of a typical sulfuric acid tank. The roof, the inlet nozzle from the tank, the structure support after is outside the tank with a 8 mm thick roof plate. A top curve angle is 100 by 100 by 100. The thicknesses given the plate width given 2.5 meters. 18, 14, 10, 8, 8, 6. So these are all the details which are required in the tank design for a 22-meter diameter and a 10-meter height tank. Self-plate material IS2062, rubber lining 10 millimeter thick, and special requirement is only because the rubber lining has to be specific for the application. So these are the details of a typical design drawing of a phosphoric acid tank. The similar drawings, of course, will be produced for a sulfuric acid application also. It's just a sample I have given here for reference only. Now, this a small discussion on health effects of the phosphoric acid, and inhalation could be a problem, or skin contact or eye contact could be a problem. Inhalation not expected to be a hazard unless heated. Skin contact is corrosive. Contact can cause pain, redness, burns. Eye contact is corrosive. Contact causes severe burns. Ingestion can burn lips, tongue, throat. Effect of long-term exposure, low concentration can cause dry, red, cracked skin, dermatitis, following skin contact, etc. Now, of course, it is not carcinogenic, it is not teratogenic, affecting embryo, it is not affecting reproductive system, and not mutagenicity, but soda contains phosphoric acid. I don't know how many of you know that the Coca-Cola that we use contains phosphoric acid, or the soda that we use contains phosphoric acid, which interferes with the body's ability to absorb calcium and can lead to osteoporosis, cavities, and bone softening. Phosphoric acid also interacts with stomach acid, slowing digestion and blocking nutrient absorption. So this was my last slide for today, except that now I have only references that we use, giving the details of each of the references. The main codes being 650 and 294. The other codes are referenced as we go along, depending on the application. And few other codes like IS we have also mentioned here, which are for the safety of the design of the tank and corrosion allowance. We can calculate using this API 581 table, which is in their part 5. So these are some of the codes which can be utilized if you are going into the actual design of a tank. And this is the end of my presentation. And thank you. If there are any questions, I am available to answer the questions. Yeah. Now you can fit